Welcome to this video on Module 3, Maskless Photolithography. We will be exploring the physics of direct write, laser alignment, and exposure dynamics on the ML3 Pro. This section covers exposure physics and the laser source, detailing the anatomy of direct write projection, optical pathways, and digital mask generation. The MicroWriter ML3 Pro uses a digital light processing engine. Over 1 million micromirrors act as dynamic modulators, projecting an entire 2D field block at once for high-speed, flexible patterning. The Optical Exposure Engine focuses UV light through precision beam shaping filters. Advanced collimation limits scattering, preserving vertical sidewall profiles, even in thick photoresists. The system supports various solid-state wavelengths, 365 nanometers for high-resolution photochemistry, 385 nanometers as the standard for common resists, and 405 nanometers for thick polymer structures. Moving on to substrate loading and laser focus, which involves precision friction mechanics, stage addressability, and dynamic height tracking. The ML3 Pro features a laser interferometer stage with 1 nanometer resolution. Piezoelectric friction drives and position feedback ensure submicron stitching across wide exposure fields without drift. To maintain precision, the system employs laser autofocus. A non-exposing 650 nanometers laser continuously measures substrate reflection to dynamically adjust the objective's focal plane in real time. Dynamic height compensation is crucial. This includes Z-height tracking, wedge and bow calibration, safeguards for chipped samples, and a static mode for ultra-flat quartz masks. Next, we discuss calibration and dose matrixing, essential for system profiling, intensity normalization, and resist-specific optimization. Different photoresists require specific energy thresholds for photolytic activation, ranging from 80 millijoules per square centimeter for S1813 to 240 millijoules per square centimeter for SU82010. To calibrate, users run a dose test. By programming an automated 2D grid and varying the dose from 50% to 150%, you can ensure perfect structural outcomes and avoid over or under exposure. Defocus optimization allows you to control sidewall profiles. Shifting the focus deeper helps with thick resists, while managing the focus offset adjusts the taper of exposed feature walls. Finally, we examine overlay alignment strategies, utilizing microscope coordinate mapping and virtual simulation to achieve submicron precision. The system utilizes various architectures for alignment, including cross and chevron markers for coarse adjustment, box-in-box targets for verification, and asymmetrical pairs to ensure correct wafer orientation. This video covers microscope coordinate mapping. The system uses an integrated infinite-conjugate microscope with Olympus objectives, paired with software algorithms to recognize patterns and perform submicron overlay registration. By measuring the precise centroid coordinates of 3 alignment keys on the wafer, the system can dynamically scale, rotate, and adjust the exposure path to match the substrate. The laser exposure sequence is a multi-step process, loading the wafer, calibrating by finding edges, auto-aligning to reference marks, locking the laser focus, and finally running the UV write process. System performance depends on lens configuration. Features range from high-resolution 0.6 micron optics with precise focus ranges to faster, 5 micron options for larger-scale patterning. To optimize your exposure yield, ensure your lens turret is correctly set. Regularly profile UV output, maintain stable cleanroom temperatures, and perform a stage flatness sweep to keep the chuck clean. Thank you for watching this module on maskless photolithography. Please reach out if you have any questions regarding the system or your fabrication needs.